Good morning, Michael.
Good morning, Matt.
We continue our journey into the wonderful world of how good is our approximation, but not linear. This time we're extending it based on what we've previously done to a polynomial. So can we start with the figure of what you mean by how good it is as reflected in the figure?
Sure. So we had this idea that if we have a function, we could do a best linear approximation, which would be a line going straight through here. But you know, this guy curves, so maybe I want something that follows the curve. So something like a parabola might be better. So that's
Sure.
second order polynomial.
Right, and in fact, if you have this, one could guess that when the curvature changes, you might have something like a cubic.
You might have a cubic. In general, you might have an nth order polynomial. And that's what we want to look at today. What is the error if you have nth order polynomial? Now, of course, you have to have a pretty smooth function. It's got to have n derivatives.
But a lot of our functions, like why are we doing this? We're wanting to approximate functions like sines, like logs, like many other things, hypergeometric functions. They're all smooth. They sometimes have vertical asymptotes. For example, the log function does, but we stay away from those.
We stay away from those. And this is a funny thing. We've been spoiled with calculators and computers because if I want to know the sign of a number, I just type in the computer and get it. But as humans, and even computers, what we really know how to do is add, subtract, multiply, and maybe divide. That's it. So if you ask me what the sign of point 1 is, I don't know unless I have a formula that somehow involves addition and multiplication.
Subtraction and division, yeah.
And that's where polynomials are handy because they're just made up of addition, multiplication.
And this is really a vectored application for calculus at the introductory level that we're looking at.
That's right. And this is really how computers compute these important functions, whether it's the sine function, hypergeometric functions, your Bessel functions. It comes
And
from
you know,
this.
it comes to me just as I'm thinking is that in the world of AI, we want to find out the fastest way to compute these. For example, square root is really important, something to the half power. So this is a really good crossover between foundational knowledge of calculus and what's currently happening in AI.
Exactly true.
So let's go.
Let's go. Okay, so we've got a function, and we say we want to approximate it by a polynomial. So a straight line will go like that. If I had something like a quadratic or a cubic, it might go something like that. Okay, so it follows the curve for a little bit, and then at some point it goes away. So this is my approximation. I'm going to call it P of x, which is a polynomial. Now what I want to know is if I evaluated x, the difference between these two guys is some sort of error. Now, Matt, you had a really neat idea, which is at each point in between here, we can have a different polynomial approximation. So at a point t here. So I'm going to write down this polynomial approximation. And what we saw is, okay, you start off with f at t, and then you add the linear term, which is the derivative times x minus t. And then there should be a second order term. So f double prime of t, and we divide by 2. And why is that? Well, because when you take derivatives of polynomials, you want to get the derivatives to match the second derivative of f. So this 2 is going to come out and cancel with that 3. So you kind of have to do that. This pattern is going to continue, and I'm going to stop at the nth order thing. So the nth derivative, we like to write it by f raised to the brackets n. That means the nth derivative at t. Instead of divided by n, I divide by n factorial. So you could think of this 2 as 2 factorial. And I have an x minus t to the n.
And I guess the point of all this is we're calling this e of t, and we can see that x is the fixed point that we may be looking at, and t is a running variable.
T is a running variable. So like you were saying before, if you imagine sliding your approximation along here, if I do the approximation here at x, well, of course, it's exactly matching x. So I get an f of x. And you notice I get x minus x, x minus x, x minus x, all those
All
are
zero. So it makes sense, right? Because we're right at the point of interest. When we're somewhere else, as t is the running variable, it's not going to be zero, and all those other terms are going to give corrections.
That's right. So now if I do it at e at x0, that corresponds to when I lined up the curve here. I could write it out. Well, okay, so this is f at x0 plus the derivative at x0 times x minus x0, and so on up to fn at x0 over n factorial times x minus x0 to the n. That's exactly the polynomial we were talking about, p of x. So what's the error, Matt?
Well, it's the difference between our prediction and the actual function of x. So it's these two.
E of x minus e of x0. Now again, Cauchy mean value theorem is our friend. How can I make this look like something like the Cauchy mean value theorem?
Well, you have to get a g. You need a g in order to do that.
Why did I call this e? Last time I called it f, but that's life.
I think we started out with e as error, but we're not doing it because we looked at e as something else. So
I'm not going to change it. I'm okay with e. So, mean value theorem said this would be the derivative of e at some point c divided by the derivative of g at some point c.
okay, so
That means I have to compute the derivative of that.
well,
Can
before
I
you do
Matt?
that, what are you going to pick for g?
I think once we know what the derivative of e is, it'll tell us what the derivative of g should be, so things work out nicely.
But can't we do it intuitively without algebra by just looking at the expression?
Okay, tell me what you think we should do.
Well, we're saying that the function is smooth. So we got linear, quadratic, then if you like, how the quadratic changes, and we end up with the nth term. So
Okay.
what we're saying is we're stopping the polynomial at n. So we're neglecting the next higher order.
Okay,
So the next higher order will be some constant times x minus t to the n plus 1.
well, that's a good intuition. So let's write that out. G of t is equal to x minus t to the n plus 1.
Yeah, and what that's saying is that that encapsulates the error, the part we neglected. It's assuming that the curve is smooth through order n plus 1 derivatives. However, the application in the background is really for functions that are smooth. We just mentioned that earlier. So this is a really good encapsulation of all that. And now we just have to algebraically work through and see where we end up.
I'm going to peek ahead at the answer and say, you remember for the linear case we had a 2 here and I put a 1/2 in front.
So 1 over n plus 1?
Let's do that.
Sure.
That way the derivative comes out as something nice. What's the derivative of this?
Well, the n plus 1 comes down and cancels the n plus 1. So we have x minus t to the power n.
And we're differentiating inside with respect to t.
So we have a minus sign.
There's a minus sign.
And look at this. What we've done is with our intuition and previous, we match that to that.
Right.
Pretty clever stuff. Let's see what the algebra does.
Well, so here's the hard part. We have to compute the derivative of this guy. Now, maybe there's a little bit of room here. Got a
That's-
derivative here.
F prime.
Now, this guy have two terms, so product rule. If I differentiate this, what do I get?
With respect to t, you just get minus f, because a minus 1 times f prime of t.
So I get an f prime of t.
And then you got to do this also depends on.
So I get f double prime of t
Oh, let's keep
times x
going.
minus t, right?
Yeah,
So this term came from here, and these two terms came from here. But the nice thing is these guys cancel, so I don't have to worry about them.
okay, take me one further.
Well, look at this. If I differentiate the minus t here squared, 2 comes out, cancels this 2 factorial, and there's a minus 1 because there's a minus here. So I got minus f double prime of t times x minus t to the 1 power. The 2's cancel.
Plus
Plus f double prime f
triple.
full triple prime of t times x minus t
Cubed. No, squared.
Squared.
Not cubed.
And look at this. This and this guy cancel.
Oh, wait.
Oh, and there was a
2 factorial.
There's a 2 factorial on the bottom. Maybe I'll put it here.
Oh, so we can see, I like the idea is that what you can see what's happening as you differentiate the next term. When you go to the next term, part of it cancels. So we've seen it here, so we've seen it here. So now we can write down what it's going to look like at the end when we're going to differentiate how many times.
So what we see is, so when the squared thing's differentiated, we got a triple square. So when this guy gets differentiated,
You're
there'll
going to
be
get an
f
n plus 1.
And that's it. So this guy is going to, so in the end, we're only left with, everything cancels except the last guy when you differentiate it.
Yeah, which is going to be
F.
f to the n plus 1 time differentiated of x
Evaluate
naught.
at some point C.
Oh, it's c. Okay, we're at c, yeah.
And this is x minus t. And remember this, see here was a 3 and here was a 2, so this is an n plus 1. This has to be an n. Okay, and what happened on the bottom? We had n factorial.
Yeah.
Okay, that,
Now,
and it's evaluated at a point C. And then we divide by g prime of c.
put it in.
Oh, we should remember our signs. Remember, we always got a minus sign. We had minus signs canceling. This one. Oh yeah, no, this is
No,
good.
that's correct.
This is correct.
Except we should have c.
Oh, you should have c.
Oh, say can you see? It comes
say
back
can you
again.
see?
The U.S. national anthem is key in all this.
Now, do you see any common terms here?
These cancel out.
So this cancels this. So this thing is equal to f n plus 1 at c n factorial with a minus sign.
Oh, so now let me jump here. If we take this and stick it over here, there's what our error is.
That's right. So e of x minus e of x0 is equal to this times 1 over n plus 1 times x minus t, x minus c.
Oh, right.
No, x minus t. Because here, it's x minus, oh, x minus x0.
X minus x0. Yeah,
X
yeah,
minus
yeah, yeah.
x0,
To the n plus 1.
n plus 1.
And remembering
And the
that,
minus signs cancel, so that's a plus.
remember one of these was 0.
And this I can rewrite n factorial times n plus 1 is n plus 1 factorial. We like to write it in a nice, neat form. N plus 1 factorial x minus x0.
To the n plus 1. We didn't explicitly, but it's clear that g of x when t equals x is 0.
Is 0, right. And that's where the extra minus sign came from.
Yep.
So
And
this
that's
is the error.
Holy, I don't want
Holy
to say
moly.
holy smoke, but it's clearly just a simple extension of what we've done previously and just some technique in using the product rule and seeing this telescoping effect when we differentiate the series, and that gives us that extra term, n plus 1 derivatives. The key mystery to me when I was studying this was, where does the g come from? And that's where that intuition of what does the next piece look like come in. Again, in most textbooks, they don't say that. They say, hey, let's pick a G.
Hey, let's pick a B, G, right.
Let's be a BG, okay. Well,
But this is the G that works. And you notice here, the way we pick G, it nicely canceled, which was a really great step. Because then in the final answer, there's no mysterious C except for in the derivative. And here's minus x naught. What this means, Matt, is, for instance, again, sine of 0.1. I know what sine of 0 is. If I put a 0.1 here, 0.1 raised to the power, say n is equal to 10. 0.1 to the 10th gives me 0.00000000001.
yeah, but 10 factorial isn't small, or 11
factorial,
is
yeah.
going in millions. So
this gives me many, many decimal places of accuracy.
So what's really interesting too about the formula is the n plus 1 factorial in the denominator accelerates the reduction of the error.
Exactly.
Except in real life, we may make errors with this as n gets big, so we don't want to get too big.
Don't want to get too big. So for instance, if x0 was 0 and x was 2, 2 to the 10 or 2 to 11 is a big number.
So that's a
So
problem.
you really need these guys close together. The other thing you have to be careful about is what's happening to the derivative. If you have a function whose higher order derivatives are big, it's going to be hard to get this small. So that's another thing to keep in mind. But that just tells you if a function has lots and lots of curves, these derivatives can get big. And so you're going to need better polynomials to...
Maybe you need something else.
Maybe you need something else. And maybe we can talk about that next time.